Hello everyone, today we are going to talk about tree sort, which is a type of sorting algorithm. Sorting algorithms are important because they help us arrange data in a particular order, which makes it easier to search for, analyze, or process that data. Efficient sorting is a fundamental aspect of optimizing many applications in computer science. Tree sort is a specific sorting technique that uses a binary search tree, or BST. In a BST, each node has two children. The left child contains values smaller than the parent, and the right child contains values greater than the parent. This structure allows us to retrieve elements in a sorted order by performing an in-order traversal. Tree sort works by inserting each element from the list into a BST and then performing an in-order traversal to produce a certain sequence. Now let's discuss the efficiency of tree sort. The efficiency of an algorithm is measured in terms of time complexity and space complexity. The time complexity of tree sort depends on the balance of the BST. In the average case, the time complexity is O(n) log n, which is quite efficient. However, in the worst case, when the tree becomes unbalanced and looks like a linked list, the time complexity can be as bad as O(n squared. This worst case scenario happens when the input data is already sorted or nearly sorted. In the best case, when the BST remains balanced, the time complexity is O(n) log n. The space complexity of tree sort is O(n), which is the space required to store all elements in the tree. Tree sort works well with randomly ordered data, but it may perform poorly with already sorted data due to the risk of creating an unbalanced.
Next, let's look at the pseudocode for the tree sort. This pseudocode will help us understand the process step by step. Step 1 is about inserting elements in a binary search tree, or BST. We use a procedure called insert. If the root is null, we create a new node with the given value. Otherwise, we decide whether the value should go to the left or right of the current node, depending on whether it is smaller or greater than the current node's value. This recursive process continues until all elements are inserted into the tree in their appropriate positions. Step 2 is performing an in-order traversal. This is a crucial part of the tree sort. The in-order traversal visits the node in a specific order. It first visits the left child and the current node, and finally the right child. This ensures that all the values are added to our sorted list in ascending order. Step 3 is the tree sort function itself. We start by checking if the input array is empty. If it is, we simply return an empty list. Otherwise, we create an empty BST and insert each value from the array into it. After constructing the BST, we use the in-order traversal to get the sorted list of elements, which is then returned as the final output. Step 4 is the main function. Here, we first take the number of elements as input from the user, followed by the array elements. We then call the tree sort function to sort the array and print the sorted result. This step ensures that the user can provide any custom input and get a sorted output, making the tree sort process more interactive and flexible. This pseudocode clearly outlines how tree sort works, how inserting elements into a tree to retrieve them in a sorted order. By understanding this step, we can see how the tree sort algorithm utilizes the process of BST to sort data effectively.
Let's look at the tree sort code. Step 1 involves the insert function, which adds the element to the binary search tree, or BST. If the root is null, a new node is created depending on whether the value is smaller or larger than the current node. It is added to either the left or the right subtree. Step 2 is the in-order traversal function, which retrieves sorted elements by visiting the left child, then the current node, and finally the right child. This traversal ensures that the elements are added and sorted in ascending order. Step 3 is tree sort function, which builds BST from input array and then performs an in-order traversal to return the sorted list. Finally, step 4. It's the main function where we take the user input, the number of elements and their values, making tree sort flexible for any custom input. The pseudocode outlines how tree sort uses BST to sort data efficiently. Now, let me demonstrate the code running with sample input. First, I'll run the code and it will prompt me to enter the numbers of elements. For example, I'll enter 6 and then provide the elements 5, 3, 7, 1, 4, and 9. After processing, you can see that the sorted input is 1, 3, 4, 5, 7, 9. This output confirms that the three-sort algorithm works as expected, efficiently sorting the elements provided by the user. This demonstration highlights how three-sort can handle different user inputs and produce a correct sorted sequence.
To summarize, today our group discussed three-sort, which is a sorting algorithm that uses binary search tree to sort elements. We talk about its efficiency, including its time and space complexity, and discuss scenarios where it performs well or poorly. We also explained the pseudocode, showed the C++ implementation, and went through a detailed example of how three-sort works. Three-sort is an effective algorithm for certain use cases, especially when the input data is randomly ordered. But it's not always the best choice when the input is already sorted due to the risk of unbalanced trees. Overall, three-sort is a great example of how data structures like binary search trees can be used to solve practical problems efficiently. So that's all for today. Thank you for your attention, and we hope that you found this presentation informative.